I'm Antonio Sala, and in this video we'll continue with the case study of checking whether a given selection of controlled outputs and manipulated inputs is right for a given purpose. We will just concentrate on the steady-state reference tracking, only with the gain matrix, and in this video we'll review the polyhedron approach. In other videos of this case study, we solved the same with singular value decomposition. It was an approximation with the geometry of ellipses. Polyhedron techniques are exact when we have actuator saturation in steady state. And in order to assess the difference between both approaches, we will graphically compare them at the end of this video. If we recall what we were doing, we had this model with 2 outputs and 3 inputs, U. Disturbances D will not be considered for the moment being. We had a linearized model around an operating point given by these values, and with this admissible increments of our manipulated variables. Non-symmetrical, but the thing is that we should move our outputs with a large enough increment without hitting these hard actuator limits. The absolute limits of the output are those here, so subtracting the operating point, we get this incremental desired limits. We must be able to attain the 4 combinations of maximum and minimum output increments without hitting actuator limits. Steady state requires only the DC gain analysis, and in singular value decomposition we scaled inputs and outputs, so the worst case maximum output minimum input was equal to 1 for each input and output. So if the minimum gain of the scaled gain matrix was above 1, then we deemed the problem as solved with the geometry of ellipses. And indeed, inputs in the scaled unit sphere were able to move the outputs in this red ellipse in the scaled output domain, which contains the unit circle. Let us now consider how to do this with the geometry of polyhedra. So basically we need to manipulate the vertices of input and output polyhedra. So first, the incremental vertices are these 4 ones, because, well, basically, if I combine the maximum and minimum of each of the desired increments, well, maximum and maximum will be 2.6, 0.15, then I will have 2.6 minus 0.1, minus 0.5 plus 0.15, and minus 0.5 minus 0.1. Those will be the 4 vertices. That's either handmade or with whatever code we wish. Here we have them. So our goal is being able to attain any output increment in this rectangle in incremental units. So we must achieve any desired output in this rectangle subject to the inputs being in between these lower and upper bounds. If we were to draw in the input space what was happening, then we would have 8 combinations, maximum, 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 minimum, and so on, conforming a sort of rectangular prism in the input space. Nevertheless, our Matlab code will not need the vertex enumeration in the input space. It will do in the output space, but not in the input space. But in order to clear things up, our objective is testing whether when this input polyhedron is multiplied by the gain, whether it maps in something, of course another polyhedron, larger than the desired output polyhedron. How can we do it? First, the easy way, if the gain was a square matrix, it will be for each of the 4 vertices computing the actual input needed to achieve that vertex. Because, okay, if G were square and invertible, that would be a single control action achieving the required output. If it were square, our input space would be also a 2-dimensional square. So if the extreme inputs do not saturate, then linearity tells me that points in between, in the convex hull to be formally rigorous, of these red output space points would map to points in the convex hull of these vertex actions. So if no one of them saturates, then interpolations between them will not saturate either. So this will be the easy way for a square system. But in our case, our system is not square. So we cannot apply the inverse. We could apply pseudo-inverse to get some sort of approximation, but in here we will apply the exact feasibility test that the Matlab command quadprog provides. What does quadprog actually solve? It minimizes some quadratic function subject to linear inequality and equality constraints. In our particular problem, we didn't have this notation, but okay, we just need to change letters. So when I see here X, it will mean input U in my particular problem. And when I see here A, it will mean G, the gain matrix in my problem. And of course, this will be the lower bound of the input and the upper bound of the inputs. So our constraints will not need any inequality restrictions other than U between these lower bounds, and this thing will end up being GU equal each of the desired vertices of my output. So as G is not square, then there will be an infinite number of U fulfilling this equality constraint. So we need to find whether any of those infinite solutions is in between these bounds, and if there is a solution, then we will output the one that minimizes this thing. But okay, as we are not doing actual closed loop control, in principle we can put whatever H and F we wish. We will just use, for instance, this lowercase f equal to 0 and this H equal to the identity size 3, so that we are minimizing U transpose U. In fact, we later on will change to the scaled U. But in here, we just put whatever H and F we wish, and we try for each one of the 4 output vertices whether this optimization problem is feasible. And this is the particular syntax that we will use. Identity 0. We will leave this AB as empty matrices. This will be the gain matrix. This will be each of the desired vertices. And in here we will have the actuator bounds. We will do that 4 times and see whether Matlab outputs a feasible or unfeasible result. Then if we go back to Matlab, I will shorten this stuff so that we can see a little bit better the whole line of quadprog, and this is the key line. Identity zeros, 2 empty matrices, equality constraints, gain times whatever input I compute should be equal to the first vertex, and the input must be between this minimum and maximum bounds. And so with vertex 1, Matlab tells me that it found the minimum that satisfies the constraints. And so it did with the second vertex, here we have it, with the third vertex, here we have it, and with the fourth output vertex. So my problem is feasible, and I indeed can find an input in between the prescribed limits that achieves the extreme values of output I need. So good, this would be the quick solution with the exact polyhedron geometry. However, we can make a pair of observations. First, regarding the optimization weights, well, as when I am scaling the SVD and pseudoinverse stuff, they actually wish to minimize the norm of the scaled U needed to achieve a particular output. I mean, my problem is solved if the unit sphere in 3D scaled input maps to something larger than the unit circle. So working with this unit sphere in scaled input, as this is the scaling, this scaled U norm is this thing, I can realize that if I put in H the square of the inverse scaling, then I will be trying to perform the same optimization as pseudo-inverses and singular value decomposition approaches to the same problem. And in fact, scaling is a must in basically all the multivariable control problems because, well, I cannot mix liters with newtons, so we need something so that when plugged into some numerical computations, deviation 1 in each of the manipulated inputs must have a comparable meaning for these optimizations to have any sense. So I would use this scaling, this input weight in my optimization problems. For this problem, if I were to use the obtained input magnitudes, or for model predictive control, which is the transient generalization of this quadratic programming stuff we are doing in steady state. So good, the thing is that this will not change feasibility, of course. It will only change which value of manipulated variables the algorithm outputs as the best one. So we will not strictly need it for feasibility, but okay, for a step closer to real applications, I will put this thing in all my vertices as the final recommendation. But as you can see, if I now execute again the code, then numbers change, and the actual meaning in technological terms of these numbers is more sensible than the previous ones. Okay, so this was the first observation regarding scaling in this quadprog stuff. The second observation is that when we discussed the singular value decomposition methodology, we had a minimum gain of 1.5, so that somehow it indicated a margin of extra safety in the sense that our unit sphere mapped onto something larger than the sphere with radius 1.49. So we have kind of extra leg room to accommodate larger output increments, if so desired, or well, maybe unexpected disturbances or modeling errors. So how can we compute this kind of margin with the geometry of polyhedra? Well, we will do it by trial and error. I will add a line of code in which my new vertices will be scaled to check whether this is feasible or not. So if I run the code again with a 1.5 scaling, somehow inspired in the values of the SVD computations, then vertex 1 meets the constraints, vertex 2 also does, but vertex 3 says that no feasible solution found, so the desired output increments are too large in this case, because there is no solution in the input space avoiding saturation. Maybe our margin is lower. If I check 1.45, vertex 1, 2, 3, and 4 are feasible, so my margin is 1.45. But if I check 1.46, my third output vertex renders unfeasible, so my safety margin, let's say, with the original increments is 1.45. So this is a way of computing the equivalent of the excess minimum gain in SVD with the geometry of polyhedra and quadratic programming. So good, I will just go back to the original numbers and we will end the video by displaying all this we have done graphically. As these were the input increments for each actuator, then this will be used to generate 8 input vertices. Then I will multiply these 8 vertices by the gain, and so I will have some points that will tell me the maximum achievable output. These points will be, in whatever disposition, I will compute its convex hull to draw a nice polyhedron. And okay, you can pause and watch the code, but our goal is understanding this graphically. The thing is that the rectangle in output space my user wishes to attain is the cyan one, and the image of the extreme input values multiplied by the gain give me the green one. So indeed, the problem is feasible. The output that all my extreme values of actuators can cover is larger than the cyan rectangle. Of course, if I multiply by 1.45, then the cyan rectangle gets larger, it just touches the edge of the green one, so larger increments of the output range are not feasible. Going back to the original scaling, the code here, you can just pause, download it from the link in the description. This code draws this same polyhedron, but in the scaled domain. So it makes the output scaling so that we can superimpose the SVD output, because SVD has no sense in non-scaled units. So what's depicted here? Well, the cyan rectangle is my actual scaled polyhedra of desired output increments. The worst case SVD converted it to the square with vertices at ±1, and the SVD approach had the goal of reaching the unit circle, which is here in dashed purple line. The outer green polygon is the same we saw in the previous figure, how my actual non-symmetric bounds map to scaled output, and the dashed, more greenish green stuff in here is what the symmetric worst case unit square in the input space maps to the scaled output space. So we see that somehow the ellipse here, which was the output of the SVD methodology, is almost tangent to that image of the cube of vertices at ±1 in input space. But of course, the polyhedron approach can exploit non-symmetry and get this larger green region in order to guarantee feasibility. So with this superposition of the scaled outputs of my exact polyhedron stuff with graphic programming, the outer green polygon encloses the small cyan rectangle, and the SVD output, which says that the orange ellipse is larger than the purple circle. Well, in this way we can make a comparative intuition of what's going on in each of the computations, and we will end up the video here. Thanks for watching.